Hello, and welcome back to the exciting world of support vector machines. So we've been talking about support vector machines, and we started off with a discussion of linear discriminants, which led to the discussion on perceptrons and the development of perceptrons, and then we identified the shortcomings of perceptrons, which led us to the motivation for support vector machines. But just to give you some historical insight, which might be very useful in framing all of this knowledge in your head. The idea of linear discriminants was proposed by a very famous statistician, R.A. Fisher, back in the 1930s. Uh, but he really didn't have a computer to solve these problems. The algorithm that led to the separation of linearly separable data on a computer was proposed by Rosenblatt in the 1940s, 50s, and early 60s even. So they implemented this idea on the computer, the idea of linear discriminants, which we now call perceptrons. Then we identified that perceptrons can give us a line that allows us to separate two classes. But the problem with that line is that it can be arbitrarily close to one of the two classes, so it does not have much margin for error. And these two scientists, Vapnik and Chervonenkis, identified that because these perceptrons give these lines that are arbitrarily close to one of the two classes or don't have enough margin, they will have poor generalization over unseen test cases, and we talked about that in detail. One of the cases that we talked about is that since the perceptron line can be arbitrarily close to one of the classes, a small change in one of the examples due to, let's say, noise will change its labels, which it shouldn't be doing. And that led us to the formulation of the same margin maximization problem, or the property that we want in our classifiers, that it should have large margins. We discussed how it relates to regularization. That is, a classifier should change its output only slightly when the input changes slightly. So a small change in the input should produce only a small change in the output. So that is the concept of regularization. The idea for that was proposed in terms of structural risk minimization by Vapnik and Chervonenkis, who said that unlike perceptrons, which do error minimization over the training data, or more precisely, empirical error minimization or empirical risk minimization, we should be doing regularization of classifiers because that can give us better classifiers which are more robust to noise and can generalize better to unseen test cases. So maximizing margin is a good thing. So the theoretical foundations for support vector machines were given by Vapnik and Chervonenkis. So they essentially formulated the main idea behind the main theoretical foundations of support vector machines. However, we were still far away from the development of an algorithm, and it took a lot of time before people were able to design an effective algorithm that can run on the computer for large data for support vector machines. And that was proposed in 1995 by together with these previous scientists that we got an algorithm in 1995 for support vector machines that worked on linearly separable data. Now, we'd like to pause here and reflect on what we have done so far in terms of formulating the problem of support vector machines. We want to do structural risk minimization, so that involves minimizing error over the training data set, which is empirical error minimization, and this is the same thing as perceptron. We want to minimize the sum of losses or the average of the losses over training examples using the hinge loss function. So this is the mathematical formulation of the hinge loss function. We have had a lecture on that, and if you're not clear about this concept, I would refer you to that lecture so that you can understand what's going on over here. What this part of the equation simply means that the product of the signs, the predicted label of an example, and its training label for a training example, their sum should always be greater than, or their product should always be greater than 1 plus 1. Whenever it is not, we give that example a penalty, or we give the line a penalty so that the line moves to a position where it does not have any such errors. And that is what this minimization achieves, okay, in a perceptron. However, unlike a perceptron, a support vector machine also minimizes this term, which is, as we've talked about earlier, the sum of squares of individual weights of the linear discriminant that is used in a support vector machine. So we are achieving structural risk minimization using empirical risk minimization or minimizing misclassifications or minimizing errors over the training data set. So that's good, that's this part. And then we are achieving regularization or equivalently margin maximization by minimizing this particular component on the left-hand side. So let's break it down and let's break this representation of the support vector machine into two parts. Let's call the right part ERM, empirical risk minimization. So this term over here. And on the left-hand side, let's call this bit, we'll call it the regularization component. So I'm going to just label that as reg. Now let's think about these two components separately. The right one, the empirical error minimization, is much simpler to understand. We've covered that in perceptron. This is what allows us to find the line that separates the two classes. So minimizing errors over the training data sets using a hinge loss function. So that's nothing new. We've talked about that in perceptron. We already have an algorithm that is simply a for loop that takes in an example, sees if there is an error. If there is, we use gradient descent to update it, and we keep on doing that until there are no further errors, and in which case we get linear separability. So we've talked about that in detail. On the other hand, we've talked about regularization and why that is important. What it essentially, this term is doing is we are minimizing the sum of the squares of weights, or in other terms, we are minimizing W transpose W, and we've also related to the square of the norm of W. So all of these things are equivalent, and what this achieves is that the weight values of the linear discriminant becomes small, and it's very simple to imagine that if the weight values are small, then even if there is a small change in the input X, then that is going to cause only a small change in the output value. So it's not going to change by a huge amount, which is the essence of regularization of what we want. But if you take both of these concepts in extremes, the empirical risk minimization part and the regularization part, they have they don't each one of them doesn't do what we want them to do. What we want. What we want is a linear discriminant that gives us the maximum margin, right? Or it achieves regularization. It achieves classification, that is, it separates the two classes, but it also has maximum margin as well. And that is not achieved by either of these components individually. Let's talk about that in a bit. If you focus on the ERM part or the perceptron part of the support vector machine, we see that solving that gives us R line, but doesn't maximize the margin, right? On the other hand, if you do regularization only, so if you forget about the part on the of the right part and focus only on the left part, then what we are doing is we are trying to minimize with respect to W 1 over 2 W transpose W. And a trivial solution of that is going to be W is equal to 0, which gives us a null line, or it doesn't give us an effective discriminant. So if you think of a line in which W is 0, which is the solution to this part, this optimization problem on the left-hand side, it doesn't effectively give us any line. Because if you now give it any x, the output is still going to be the product of W transpose x is still going to be, the discriminant function score is still going to be only the bias term. So it's not going to give us anything. It's just going to give us the bias, which doesn't give us the classification label. We'll not be able to use it in practice. So now what we've done so far is that out of the two, each one of us, each one of these terms does not do what we want. However, putting these two pieces together achieves what we want. If we solve this optimization problem in which we have regularization and we have empirical risk minimization, then first of all, because of the empirical risk minimization component, we get a line that separates the two classes because we are trying to minimize misclassification errors over the training data set. And at the same time, we are achieving regularization by introduction of this term on the left-hand side. And this term is very important. This hyperparameter C is very important because it controls the compromise between these two terms. If you set a very high value of C, then what you get is essentially a perceptron. It's not going to pay much attention to the left part of the optimization, so it's essentially going to turn into a perceptron. If you set a very low value of C, then you won't be able to achieve discrimination, because if you set C is equal to 0, for example, what you get is a null line, W is equal to 0. So that's not going to achieve anything. So choosing the right value of this hyperparameter C is very important. And I hope you have a good understanding of the role of this hyperparameter C now. Equivalently, in some books or in some texts, you can see an alternate representation of a support vector machine in which there is no C term, but what we have, and we've developed that as well, what we have is a term, is a hyperparameter called lambda, which gets multiplied with the weight vector. And then we simply have a summation over the hinge loss function. So I'm just going to call it loss function, f of xi with yi. Okay. So these two are equivalent representations of the support vector machine. So don't be confused if you see one in some books and the other one in some papers or books. So don't worry about that. It's just the role of C and lambda is the exact opposite. So if a large value of lambda corresponds to a small value of C and vice versa. Okay. So I hope you now have a good understanding of support vector machines and the role of the hyperparameter C. I welcome you to read more about the history of support vector machines at this link that is given at the bottom of your screen. So you can familiarize yourself with how it emerged. And as you can see, it took a long while for moving from a linear discriminant to uh, to the formulation of the support vector machine algorithm that we have coded in our previous slides. And one of the problems with this support vector machine algorithm is that it still is based on a linear discriminant. So based on something that was proposed by R.A. Fisher back in the 1930s. We haven't really, what happens when the data set is linearly non-separable, or what happens once we have a very large number of dimensions and so on. So we want to solve that problem as well. And that problem was solved by contributions from a number of scientists. So of course, all of the scientists that you see on your screen. But there was a major shift from these linear discriminants to nonlinear discriminants through the introduction of what is called the kernel trick, which was proposed in the 1990s by Sholkov and others. So we are going to talk about that in this lecture series as well. And what that allows us to do is, it's a really simple concept once we get to it, but what it allows us to do is that it allows us to get linearly separable lines. So I hope this historical aspect of support vector machines would have also strengthened your understanding of the role of hyperparameters, the role of regularization, the role of empirical risk minimization, and of course, structural risk minimization in overall. Thank you.